Good afternoon. Today we will continue the lecture on mass storage. Last time we talked about file arrangement. Here you have explanation what is a byte sequence that is typically called serial file, sequential file that is sequence of records, and tree structure file. It has a B-tree like arrangement. It is not strictly B-tree because B-tree has the lowest level always filled. In Unix and Windows, we have only those files, but in other operating systems, you can find sequential or indexed files. It is like B-tree with n equal to 3. And the file has a directory entry that describes this file. It can have many useful information, like who is the owner, what are the rights to access this file, when it was created, where the file is on the disk, what is the size of the file, and so on and so on. Those entries, I don't know if they are all from given operating system. It's just enumeration of typical information. Some operating systems, including Windows, allow using files in memory. They are called memory mapped files. I don't know if they are in Linux. But in Windows, you can declare such file. Such a file, generally, in Windows, every program gets maximum address space of maximum possible address space. That is only partially filled with pages. And some scope in memory can be reserved for such file. When we open such file, it is loaded to memory from disk. All updates are made in memory and all reads are from memory, so it's extremely fast. And on close, it is written to the disk. Here we have example. We have two memory areas of program and data. And additionally, we have file ABC loaded to memory and new created file XYZ. So it has some address, but it does not contain data because it's a new file. On close, if there are temporary files, they are discarded. If they are to be permanent, they are written to the disk. How the files are arranged on a disk? In directories. Of course, first manner of accessing the devices, especially random access devices, was just read or write given sector or block. Of course, it was not convenient just naming the files with their block number. There were no files those years. There were just informations on a disk. And especially if we write, we can overwrite some useful data accidentally. So the engineers invented symbolic names that identify a given area on the disk. And those names should have been stored somewhere. So natural solution was a catalog of files. In modern solutions, catalogs are files themselves of special treatment only. But formerly, there were solutions in which catalogs were just separate beings. And the main purpose of directories is to map between symbolic names and location on the disk. Here we have three example structures of directories. First two are our historical. No, first two are of historical value. Simple structure is just a catalog of files, nothing more. Second is a catalog of users, and every user has its own catalog of files. And nowadays we use hierarchical structure in which we have a tree or a structure that is almost a tree with file names, paths, the notions of current directory, relative path, and so on. I think that you know it from your practice. This is simple structure with single directory. The letters are users, not files, because two files cannot have the same name. So we have 4 files owned by 3 or more. Well, here we have 3, 2 or more. Here we have 3. This is 2-level structure with root directory and user directories. And here we have typical hierarchical structure with many levels of catalogs. This is the root directory, user directory, or system directory, subdirectories, and files. It is a tree. And for example, in Windows, it is actually the tree. However, in Unix-like systems, we can make links more than one to the file. This technique, I think, is seldom used nowadays. It was invented to save the disk space. Instead of copying a disk to another user, it was easier. It was not easier, but cheaper to make a link. It was not a good solution because I think that Unix structure is overcomplicated, and it is source of many problems with restoring data in case of data corruption and so on. You will see on next slide how it works. So it is a cyclic graph in Unix-like systems. This is the physical structure of some tree of directories. Not only Unix. We have root directory that has names and locations of second level directories, maybe files. We can put files in root directory. This directory has pointers to third level directories. Here we have name and pointer, not shown in the picture, to directory, next level directory, or maybe a simple file. How the files are allocated on a disk. Seldom used continuous allocation. It is seldom used, but it is very simple because the file occupies a compact area on a disk. So such solution is used in simple file systems for IoT. Chain allocation is arrangement of a map of all blocks on a disk. Those blocks are allocated to files, and a chain is arranged among them to show where the file is on the disk. The head of this chain is outside, but it is in the directory, in the directory entry. But the rest of the chain is in FAT. FAT is file allocation table. So in catalog, we have a root, starting block, and size. In each block, in FAT description, not in each block, in each block description, there is a pointer to the next. Index allocation, I will show it later on next slides. Here we have continuous allocation. We have 7 files that occupy continuous areas on the disk. There is a free block at the end. And after deleting 2 files, D and F, we have 2 holes, so their positions in the catalog are changed to holes. This is a block number and block count. This allocation is not used nowadays because it occupies part of a block for a pointer. So the block content is not strictly 2 to the power 2 to some power, because some bytes in the beginning are used to arrangement of a list. So it's historical. Now, similar chain, but not in file itself, the chain in FAT. We have data in the directory that about the head of the list. So the information that file A starts here in block number 4. And we have a chain 4 points to 7, 7 points to 2, 2 points to 10, 10 to 11, to 12, and 12 has a tail of the list, which is -1. File B starts in block 6, and again we have a list that finishes in block 14. Some special values with minus, of course, because positive values are elements of chain. Negative values can specify booked, reserved for some activities of operating system, dematched, not to write in this block, free, some special values. In Unix, the disk, the file is described by special data structure called inode. And we have a table of inodes on the disk. The inode specifies some set of attributes with the owner, date of creation, access rights, and so on. And location on the disk, how the location is defined. We have 10 pointers to blocks containing a file. 10 pointers. It's not much. So if it's not enough, we have a indirect structure, indirect addressing structure. We have a block that contains pointers to blocks. If it's not enough, we have double indirect allocation. We have a pointer to the block that points to the blocks that point to final blocks. Of course, data are stored only in those leaf blocks. And if it's not enough, we have triple indirect addressing. And more. There is no quadruple direct addressing. In this structure, the size of a file is limited. We have 10 plus block size divided by disk address size, plus the same squared, plus the same cubed. It is large value, but it is finite. On some small disks in the past, when the blocks were small, this was a limitation. There were some cases in which people reported that they cannot enlarge a file, but they have a space on the disk. Nowadays, the block size is so big that this structure accommodates to needs of users. Directories. How directories are built? In Windows, we have a list of directory entries. Each of them contains a set of attributes. Among them is the name of the file. It's one of the attributes. It is distinguished to show the difference between Windows and Unix. Because in Unix, directories contain only the name and inode number. Two fields, name and inode number. That is treated as a pointer, but it is an index in the table. Data structure containing the attributes, it is inode simply. The Unix disk contains several areas. Superblock defines other areas, not only. For example, for inode table, it defines the size of inode table, but additionally, number of free inodes. Pointer to first free inode, because the list is threaded to free inodes. So there are data in Superblock about arrangement of the disk partition, in fact, not the entire disk, but disk partition. Because inodes define the location of the file, and directories themselves define names and link to inodes, the resolution of a path is not so easy. Let's look how it is done. We read root directory, that is slash. It has a inode in constant position. In every Unix disk, it is in the same position. It says where is the main catalog root in data. Typically is in the beginning, because when we create a new disk, we create root directory on empty data area. So typically it occupies the beginning. But initially, because when we add new files and we want to expand the root directory, the continuation blocks can be in arbitrary places in data. So only the beginning is here. Only beginning, and typically we don't have so much files in root directory. So typically it is entirely in this position. we read root directory, searching for the name USR. When we find it, directory entry tells us what is the inode number of USR directory. It is somewhere here. Okay. So we learn about the location of USR in data, and we move to data. When we read the content of USR directory, searching from AST. When we find AST, we have inode number of AST, and we read the block number containing AST. It is somewhere in data. In those data, we search for name mbox. And directory entry defines the inode number. From this inode, we learn where mbox is in data, and we can start reading mbox. So you see that the heads of the disk, while this name resolution is performed, they move left and right, left and right. Yes? Inode data, inode data, inode data. It's not very convenient. In Unix version 7, a new structure is added, segments. Segment of the disk has its own inode table, its own data. So the catalog, the directory entry, must have additional element. It is segment number. Typically, the file is allocated in the same segment where is its parent directory. The file is allocated in the same segment that directory that points to this file, but not necessarily, because the idea of this is to keep different allocation unit size in those segments. Small blocks for small files to save on internal fragmentation, and large blocks for large files. But special treatment can allocate a file in data of another segment. Just this S is changed. This structure can lead to some phenomenon similar to fragmentation. We have two segments. Assume that inode table is full in segment 1. We have 3 blocks in segment 1, but we cannot allocate a file because inode table is full. And here we have a free inode, but we have no free space in data. So we have inode, we have space in blocks, but new file cannot be allocated. Just for your information, you need not learn it. These are the data in superblock of Unix version 7. Number of free inodes, index of the first free inode in the list, size of inode table, size of data area, and so on and so on. And additional information. Let's look how this multi-link structure is arranged on the disk. We have a file which is described by an inode. This is the inode of this file. We have the directory here that has information about this file. That means that it has a name and this inode number, and name is X. So here in this directory, there is a position X with this inode number. Assume that in the second directory, the file name is Y. It's different. It can be different. So we have the entry with name Y and the same inode number. That's why the names in Unix are not stored in inodes. All data except name, because name is held in directory. We can make another link to this file in the same directory, for example, with name Z, that has name Z and the same link to the same inode. They all point to the same inode. And the inode defines position on the disk when the file is allocated. So inode does not contain a file name. This leads to, generally, the structure of Unix disks leads sometimes to some non-expected situations like that. Assume that we have a file in our directory. We are the user C. We have a directory pointing to a file. It has some name, not important. And it has in inode, the owner is us, C. And count link, which is necessary, I will show you why, is set to 1. And this inode defines the placement of this file in data. Okay. I make this file available to other person via link to the file. It's user B. And he has my file in his directory. The owner did not change. It only changes the link count to 2. And the position of the file on disk does not change. I remove this file from my directory. It stays only in directory of user B. But the owner still is C, Nobody changed it. Especially, do you know how access rights are displayed in Linux? 6 letters. RWX, 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 and those who are not granted are replaced by minuses. Okay? Assume that the access rights to this file are RWX and no more. It happens. So user B can only see a file, but he cannot read this file. He cannot erase this file because the owner is C, and the owner has those rights. Of course, the root user, supervisor, can do something with this, but user B cannot do anything. Oh, assuming that we have this right, user B can read, but cannot write, and cannot erase the directory because it contains a file. So when it is this rule is the reason why the canceling on a file in Unix is called not erase, not cancel, but unlink. The operation is called unlink because we simply remove a single link, but other links remain. When B is able to erase this file, it can do it. So for a while, the link count drops to 0. And if it is 0, the operating system can cancel the file. This is the resolution of the name that I mentioned earlier, USR ASTM box, shown in detail on the disk. When access to given inodes and block numbers is shown. In Tannenbaum, it is not full because this and this operation is not shown, only the middle. But it's natural that we start always with inode 2 when we make the resolution. We start from inode 2, we learn where the root directory is on the disk, typically in 0 block, because root directory is created when new disk is created and it is empty. So it is typically 0. And we read the block 0, which contains root directory, and we search for USR. Search. Yes, there is USR. So we have those directories that we mentioned before. It is inode number and name. 2 first directory entries are special because they define this directory, dot is this directory. So if it is inode number 6, inode 6 is the, describes this file. Here we have 6. And 2 dots is the parent. So it is the inode number of the parent. First level directories have always 2, because 2 is the index of root directory. And because root directory does not have a parent in the tree, it has 2 times 2. In original Tannenbaum slide, it was 1 here, but it is not true. Inode number 2 is the root, not number 1. Inodes 0 and 1 are for special purposes. So we found USR. It defines inode 6. So we read inode 6. And we look where the file is in data. It is in block 132. 132. We read this block, and we read the content of USR directory, searching from AST. Yes, it is. inode 26. We read inode 26, and we learn that the file starts in block 406. We read block 406. It is AST directory. And we look for a box in this directory. It is inode 60. We read inode 60. It defines the attributes and position of file USR AST mbox. It begins in block 608. Now we can read the file, block 608. Okay. It is quite different. In fact, I showed you the chains of entries in FAT that define the position of the file on the disk. Those entries in FAT are very small. In Windows, the FAT structure had the name FAT. The name of file system was FAT. Nowadays, typically, we use newer structure, NTFS, that is elaborated by Novell company and bought by Microsoft. And typical modern disk use NTFS, but of course Windows understands and can use FAT. There are 3 versions, FAT12, FAT16, and FAT32. The name of FAT, the number in name of FAT is just the size of position in FAT. 12 bits or 16 bits or 32 bits. So always the head of the list in directory entry, and the rest is defined in fact by the chain of references to blocks. The chain is here. This structure was not free from errors because they assumed that main directory is in known place, so we need not describe main directory in FAT. And the chain for main directory was not established. What is the effect? When we enter large number of files in root directory, we cannot enlarge this directory because we have no chain to which we can add a block. Today, a student in Polish version of this lecture told me that now he understands why from time to time he cannot allocate new files on his disk, because it is elder disk with FAT, and the FAT in this disk is has 512 entries, and he cannot allocate a single file more because of some stupid decision not to represent main directory in FAT chain. In fact, Microsoft allocates two versions, two FAT and copy of FAT, two incarnations of FAT. It was prepared to future recovery, but Microsoft allocates second FAT, but they do not use it. It's prepared for future, but not used. Again, this decision was not clever, because if the beginning of the disk is corrupted, both copies of FAT disappear. There are commercial programs that allocate third FAT at the end of disk, and it has the sense. Because in a case when beginning of this is corrupted, we can restore something from the copy of FAT there is at the end, and is kept up to date. Okay. Let us return to chains. Mm-hmm. Oh. Oh. When you click the disk icon with right mouse button, you have some options what to do with disk, and there is disk creeper option. For example, if you remove a flash disk from the slot too early, the structure can be corrupted. And this utility can repair such a disk. And two typical situations discovered by this application are lost chain and crossed chains. How can we describe those two situations? What is lost chain? We have a chain of entries in FAT, but no directory entry contains the head to this chain. It is orphan chain, we can say. it is reported as lost chain. Maybe the file was cancelled and the chain was not deallocated from FAT. Maybe the file is written to the disk, but directory entry was not made to this file. We don't know, just lost chain. Typically, such a disk repair utility converts this chain of blocks to a file, giving it the name, for example, file 0001. And the user can look at the file and decide if to cancel it or to keep and give it proper name. The second situation is cross chains. It happens when some chain head or chain position, two chain positions, or a position and head in directory, or two heads in directory entries, appoint the same entry in FAT. It cannot happen. The file cannot be appointed by two directory entries, and two files cannot have a continuation, a common continuation. So this is some corruption. I don't remember how it treats those cross chains in disk repair. I think most clever is duplicate the file from the position when the chains are joined. To have two separate files with the same continuation starting from some point. But I don't remember what this utility does actually. Okay. Here I collected the limitations provided by the structure of Unix and structure of FAT. This equation we know already. It is the size of maximum size of a file in Linux. But in FAT allocation, the file can occupy the entire disk. There's no limitation. And the limit for number of files, in Unix, it is the number of inodes in the table, not a single file more. In FAT, every file can occupy different block, so we can have as many files as we have blocks. It has some limitation. I remember it was, it was very, very long ago. I had a disk of capacity half gigabyte and FAT16 structure. It is not enough. It was not enough for me, so I bought a disk of 1.2 gigabytes, more than twice size. I started to copy data from my old disk to the new one, and the system reported insufficient disk space. Why? This disk is larger. Okay? I erased this new disk and started again, and the situation reoccurred. Why? What happens? Let us analyze. FAT has fixed size on a disk. So the block on the disk depends on disk size. Having the same number of entries in FAT, when we have 2 times larger disk, we have 2 times larger blocks. Okay, and because the blocks are 2 times larger, I didn't have 2 times larger blocks, because starting from half gigabyte and finishing in 1.2, I crossed 2 borders of half gigabyte and 1 gigabyte. So my allocation units were 4 times larger on the new disk. And number of them was, if the disk, if the allocation unit is 4 times larger and the disk is 4 times larger, everything is okay. But allocation unit was 4 times larger, but the disk was 2.1 times larger. Okay? So my data couldn't be copied to this disk. So those structures have some traps that are not easy to imagine. Okay. Some systems, including early versions of Unix, use such dynamic structure for keeping free space on disk. In FAT, it's simple. A FAT entry with value -1. But we have no FAT on Unix disk. We have something similar because in modern disks of Unix, starting from version 5, maybe, or 3, I don't remember, we have a map similar to FAT, but only 1 bit per block. If free, 0, if occupied, 1. But previously it was a chain of 3 blocks. And this chain was organized such a way that we have 3 blocks that have pointer to another 3 blocks. Those 3 blocks have pointer to those ones. First and last are reserved for creating a list, two-way list. And the rest for appointing 3 blocks. Imagine what happens when we add a new block. Connecting a new block. If for example, previous from last entry is 3, we use this entry to appoint this block. It's easy. And we connect a new block. This is full, we assume. What we do, we chain the new block to the list. One more block is connected. It takes first entry of the new block. when we remove okay. When we disconnect, we cancel the last entry. If the block becomes empty and we disconnect, we cut the list by one block. The next one is taken from this position. This structure disseminated the content of files roughly on the disk. So it was not easy to maintain in the case of some error on the disk. So they switched to a map of free blocks on the disk. In Unix, external devices, disks, and all other devices are described as files, special files. They are called special files. And they are put in special directory called def. In such directory, of course, those inodes of those files do not describe position on the disk. They define
这些空闲块中间就说明是类似于磁盘碎片，是吗？
Please mute your microphone, okay? Maybe. What I said, they define the driver.
但是现在的固态硬盘是不需要清理磁盘碎片的，这是属实吗？为什么呀？
Please mute your microphone. How it is arranged. Every driver of a device gets a driver number in the system. And this driver number is a major number for all devices, the devices supported by this driver. So we have a disk, keyboard, screen, a teletype for remote terminals, TTY, maybe floppy disks or CD-ROMs, whatever. Every device, mouse, every device has a driver, and it is the major number of a device. The minor number is a number of devices of the same type. So we have, if we have 3 disks, they will have the same major number and different minor numbers. And this number is a number of data structure describing given individual disk in some table inside operating system. Oh, I lost my pointer. And special command make note creates a new device. Of course, we must have special privileges to do that. This is how the space of a disk, actually not disk, but a partition of the disk. Because on the disk, we can have many partitions. Some of them can be Unix-like, some of them Windows-like, NTFS or FAT. So every disk has a structure called master boot record. It contains a partition table. This partition table defines what are the partitions on the disk. There can be maximum 4 of them. Such a decision was made a long time ago. And this table contains only 4 positions. Unix partition, it has a pilot to load operating system. It looks at this partition table. At most, one partition can be marked as active partition. This is partition from which we load operating system in boot time. The beginning of partition contains a boot block that continues loading operating system, but given operating system. This is universal and directs to boot block of given partition. And this is specific to, for example, these two. This is specific to Linux. Then super block is on the disk. It is data that we discussed already, the organization of the partition. It is contained in super block. I don't know why Tannenbaum separated it. Free space management. It is this table of bitmap of free and allocated blocks here, but only for data area, for this area, Inodes are treated separately because it's a table, so we know the size of this table, and free inodes are threaded to some list, and in super block we have the pointer to first free inode. Then data area, there was a solid line here by Tannenbaum, but I made it dashed line because root directory is in data area. More, if it has continuation, it is not at the beginning, it is somewhere among other blocks. So I modified this and I added this data area. Okay. So it finishes our discussion on the structure, static structure on the surface of the disk. But now we will discuss what structures operating system builds to access data that are on the disk. When we click the file manager in Windows, a window opens that contains the list of files in some directory. Typically, it opens the directory of documents of given user. So we think that operating system knows all those data, and we only click and that it displays those data. It sees the entire disk, all data on it. It is completely false. Operating system collects the minimum data that allow operating system to navigate between those data. We can say that operating systems look at the disk through the mail slot. So narrow mail slot, which is only those data needed to display them or to offer them to the program for data input and output. So on the disk, we have directories, files, and access rights that are static. Oh, we can change them, but given time, they are static. In operating system, we have procedures for searching the directory, for opening files, for acquiring effective access rights. Access rights are not so simple. In Unix-like systems, we have those RWX. However, we can open a file that we have right to write, but we open the file in read-only mode, so we cannot write. In Windows, we have additionally the rights inherited from user rights to the directory containing a file. Some of those rights are inherited. So we have minimum of 3 elements. Rights of user to given directory, rights in the directory as attributes. In Windows, we don't have 9 rights, we have only 1, read-only. But it is smaller number, but it works the same. And the mode of opening given file. Always the lowest of those rights are taken as effective rights, so-called effective access rights. They are the smallest of those 3. Data structure that support those procedures are shown on the screen. On the left, we have all inodes of all files that are being touched. When we run the program, operating system opens the file, reads this file to memory, and closes the file. So when the file is being loaded, the inode of this file is in this table. When the program opens a file, we have the inode of this file as long as until the program closes the file. It is in this table. a special treatment is for mounting devices. Do you know what is mount? Mount operation. I don't remember the order of parameters, but we provide the empty directory and a special file. For example, floppy disk 0. I know that you don't use floppy disks, but I used to use floppy disks. What happens? We have the structure in, why it is needed. In Windows, every device has a letter, A, B, C. Typically, C is system disk. Why C? Why not A? Because when IBM introduced IBM PC with hard disk, A and B were reserved for floppy disks. So hard disk was C, and operating system operated mainly on hard disk. That's why we use C, but it's not fixed. We can use another letter for system disk, but typically it is used C. There is no such mechanism in Unix. We have single tree of files and directories. It is on default disk. So if we use other devices, we must mount them. So I have my directory, user is general directory, my directory, and X directory. There is a condition that X must be an empty catalog. I don't know why empty. It would work even if it's not empty. But they decided that it should be empty. Okay. And on floppy disk, we have the same structure of superblock, inode table, and data. So we have the same structure of directories. For example, A, B, C, and root. And after mount, every access to X is access to the root of this device. So we can write USR WBD A. It is this file. For the time when the device is mounted, inodes of those two directories are kept in active inode table to resolve these references. So the inode of X and inode of root of the floppy disk are kept until we unmount this device. There is one inode that is always kept in this table. What is it? Root directory of main device, of main disk. It is always kept in this table. Okay. What time? Let us analyze the connections of those tables. This is for inodes. But we can open a file that is described by inode. And we can open this file many times. For example, if two applications cooperate, one of them can write to a file and the second read from the file. So there is a system table of open files. But the name is misleading. It should be named table of openings, not of open files, because open file is described in inode table. Every open operation creates new entry in this table. So it is not a table of files being open, but the table of openings. And there is not only a way of using a file to open it. We learned about fork operation previously. Fork operation copies all data of the process, including system data. This file is in system data. So the clone has access rights to all files opened by the parent. That's why it can read from keyboard or write to the screen. There are special files, of course, but files. So the second way of accessing the file is inheriting the file from the parent. So it is use process open file table, but it should be used a table of uses of files. This is table of openings, and this is table of uses of the file, of a file. First, let's look how left-hand table cooperates. Every file that is mentioned somehow in operating system, so it is root directory or a program started to run or file opened by the file, inode is in this table, is loaded to this table. But we can have inode number 5 on more than one device. We can have inode 5 on system disk and inode 5 on floppy disk. So this field resolves. It is inode of the number 12 from disk number 2. So we know from what device the inode is loaded. And we have a opening count in active inode table. And we have those files open. First is opened by user X with those rights. Effective rights are written here. Because if I want to write, operating system checks if I can. I can if I have this right, effective right, written in this table. And number of handles. What is number of handles we will discuss later. And this file is opened 2 times, but by user Y. so we have open count equal to 2. Let's look what happens if we open file D. New entry is created in ActiveINOD table, and new entry is created in system table of open files of user X with given rights. But if we open file C, it is open already. A new entry is made in system table of open files, but here we only increase the open count for this file. This picture shows how the right-hand tables cooperate, but now we finish our today's lecture. Okay, thank you, and see you next week.